In this video, I'm going to solve the fourth problem from chapter 19. When 22.5 joules was added as heat to a particular ideal gas, the volume of the gas changed from 50 centimeter cube to 100 centimeter cube while the pressure remained at 1 atm. By how much did the internal energy of the gas change? If the quantity of the gas present was 2 multiplied 10 power minus 3 mole, find Cp and Cv. So here in this question, we have to find three answers. So this question has three subdivisions. So we have to find three answers. So before, we have to know what is given in the question. So first of all, I'm going to write the given. So in this question, they gave the heat. So that means you are adding some amount of heat to an ideal gas. And its volume get changed from 50 centimeter cube to 100 centimeter cube. And you have to maintain the pressure as a constant because the pressure here is not changed, which is 1 atm. So if you want to solve the questions, we have to convert this atm to Pascal. Clear? Okay, now what I'm going to do, first of all, I'm going to write the given. So amount of heat energy supplied to the gas here is mentioned as 22.5 joules, right? And by that, its volume changed from initial to final. So Vi takes the value of 50 centimeter cube. So if you convert it in terms of meter cube, which is 50 multiplied 10 power minus 6 meter cube. Likewise, the final volume here they mention as 100 centimeter cube. So which takes the value of 10 multiplied 10 power minus 6 meter cube, right? And the pressure is a constant, so they mention it's 1 atm. So if you convert this atm to Pascal, you have to multiply this number with 1.01 multiplied 10 power 5. So what you have to do, 1 multiplied by 1.01 multiplied 10 power 5. When you multiply this number with the number of pressure, you will get the answer in terms of Pascal. So here the answer, which is nothing but anything multiplied by 1, will be the same answer. So 1.01 multiply 10 power 5 Pascal. So now what we did, we convert the atm value to Pascal. And the number of gas, the number of moles here they mention N, which is equal to 2 multiply 10 power minus 3 mole. So all these values are given in this question. So by using this value in the first part of the question, we are going to find what should be the change in internal energy. So we are going to find the internal energy change. And we studied in the theory, for finding the internal energy of the gas, we have to use the first law of thermodynamics. What's the first law of thermodynamics? As we studied, the amount of energy supplied to the gas, which is equal to change in internal energy plus work done, right? And here we are going to find the internal energy, so we have to rearrange this equation. Therefore, the above equation will become internal energy change, which is equal to heat minus work done. Now we have the value of the heat here, but the most important thing, we have to find out the value of the work done. So in the questions they clearly mention the pressure is remain as 1 atm. That means here the pressure is constant, but the volume get changed from initial to final. So when the pressure is constant, we studied the relation for finding the work done, W, which is equal to P delta V. So if you expand this equation, which is P multiplied by V final minus V initial. Now what I'm going to do, first of all, I'm going to find the work done, and then I'm going to substitute the work done here for getting the answer for the first question. So let's we find the value of the work done. So the pressure what we have here is in terms of Pascal, which is 1.01 multiplied 10 power 5, and the final volume here is 100 multiplied 10 power minus 6 minus 50 multiplied 10 power minus 6. So if you calculate this value, you will get the answer as 5.05, and the unit for the work is nothing but joule. Clear? Okay. Now what I'm going to do, I'm going to take this value and substitute here, and the value of the Q already given in the question as 22.5 joules. So we have the value of the Q here. So once you substitute the value here, we will get the answer for the first part. So now what I'm going to do, I'm going to substitute the value of the heat energy here. So heat energy here is 22.5 joules and the work done we have is 5.05. If you subtract this value with this 5.05, we will get the answer for the change in internal energy as 17.45 joules. So this is the answer for the first subdivision. Clear? Okay. Now we have to find the value of Cp and Cv. As we already studied the definition for molar specific heat at constant pressure as well as constant volume, we know the rule, which is Q equal to NCP delta T. We studied this rule, right? Now we have to rearrange this equation for getting the answer for the B part, which is Cp, right? So we have to rearrange this equation in terms of Cp. Therefore, the molar specific heat capacity at constant pressure, which is equal to Q over N multiplied by delta T. Now we have the value of the heat energy as 22.5 joules in the question, and the number of moles also given. But the most important thing, the delta T is not given in the question. But they gave the information, the gas, the amount of heat energy supplied to the gas here is ideal gas equation. So what I'm going to do, I'm going to use the ideal gas equation, which is PV, which is equal to nRT. This is the equation for ideal gas. But the most important thing here, the pressure is the constant, but the two things are variable, which is delta V and delta T. If you rearrange this equation in terms of delta T, we will get the rule, and I'm going to substitute that delta V here. So let's rearrange this equation in terms of delta T. So by that, the above equation, this equation will become delta T, which is equal to P delta V over N multiplied by R. Now I'm going to take this and substitute here. By that, this Cp equation will become Cp equal to Q over N multiplied with P delta V over NR. So this N and this N get cancelled and this R will go to the top, right? By that, this equation will become Cp equal to Q multiplied by R over P multiplied delta V. Now we have all the values, right? Here R is a gas constant and Q is the amount of heat supplied to the ideal gas and P is the pressure, which is a constant pressure, right? And delta V, we have both final volume as well as initial volume. And once we substitute the value here, we will get the answer for the second part of the question. So now I am going to substitute the value. So the amount of heat supplied to the gas here is 22.5. Multiply with the gas constant 8.314 over, and it's a constant pressure, so in terms of Pascal it's 1.01 multiply 10 power 5, and delta V final is 50 centimeter cube, and sorry, final is 100 centimeter cube and initial is 50 centimeter cube, and when we subtract 100 with 50 we will get 50 centimeter cube, but centimeter cube in terms of meter, which is 10 power minus 6. Now, if you multiply both top and bottom and divide, you will get the answer for Cp. So once you substitute the values, multiply top and bottom, I got the answer as 37.04. And what should be the unit? The unit here is joules over mole Kelvin. So this is the answer for the second question, right? Likewise, we have to find the answer for Cv, and for that, I'm going to use the rule as we already studied in the theory, Cp minus Cv, which is equal to R. So now I'm going to rearrange this equation in terms of Cv. Therefore, Cv, which is equal to Cp minus R. So Cp we already found in the B part. So I'm going to take this value, I'm going to substitute here. So if you substitute, what will happen? Cv equal to 37.04 minus the gas constant is 8.314. So we will get here, when you subtract, so when you subtract the value 37.04 with 8.314, we got the final answer as 28.6 0.73. And what's the unit? Again, the unit here is joules per mole Kelvin. So this is the answer for the third part. Clear? That's it. Thank you.